Galaxies that broke physics. The best model we had for how the universe works took decades to build, survived every test we threw at it, and explained everything from the cosmic microwave background to the formation of stars. Then, Webb spent 6 weeks staring at the early universe and quietly broke it. It didn't just find one exception, it found dozens. In Webb's very first deep field images, astronomers spotted massive, fully formed galaxies existing when the universe was only a few 100 million years old. Galaxies so developed, so heavy, so structured that they shouldn't have had enough time to form. The universe was barely 3% of its current age. These weren't small proto-galaxies either. Some of them were as massive as the modern Milky Way, meaning they somehow packed billions of years of growth into a sliver of cosmic time we thought was still basically empty. Scientists nicknamed them universe breakers, which is a real thing astronomers actually said out loud in published papers. The leading cosmological model, called lambda CDM, predicts that large galaxies grow slowly through billions of years of mergers. What Webb found in week 1 suggests that either galaxy formation can happen dramatically faster than we thought, or there's something fundamentally missing from the model itself. We genuinely don't know which. That's not a hedge, that's where the science is right now, and the model in question is the same one we use to predict where the universe came from and where it's going. A teaspoon of doubt in that framework ripples into every cosmological calculation we've made for 50 years. Stars born in violence. Most people picture starbirth as something quiet and gradual, a cloud of gas slowly condensing under its own gravity until it ignites. Webb's images of stellar nurseries suggest the reality is considerably more brutal than that. And the thing that makes it weirder is that stars are actively killing each other before they even finish being born. Webb's image of the Carina Nebula's cosmic cliffs region shows jets of superheated plasma firing out from protostars that haven't fully formed yet. These jets slam into nearby gas clouds at thousands of miles per second, and when they hit neighboring protostars, they can disrupt the formation process entirely, essentially destroying a star that was still being assembled. Birth out here is not peaceful. It is loud, violent, and frequently fatal for the neighbors. The cliff face in Webb's photograph is 7 light-years tall. To give that scale somewhere to land, 7 light-years is about 41 trillion miles, roughly the same as flying to the moon and back 87 billion times. The structures carved into the gas and dust are formed by ultraviolet radiation and stellar winds blasting material away in real time. Birth, apparently, is extremely violent out here. Nothing gets to just quietly arrive. The universe accelerates. Here's something that should genuinely keep you up at night. We don't know how fast the universe is expanding, and the two best answers we have disagree with each other by an amount that can't be explained away as measurement error. Webb was supposed to settle this. It didn't. In fact, it made the problem harder. The Hubble tension is a crisis in cosmology, where measurements of the expansion rate from the early universe and from today keep coming out differently. Webb was built partly to refine the modern measurements using Cepheid variable stars, stellar lighthouses we use as precise distance markers. Webb did refine those measurements. The tension didn't go away. If anything, Webb's data suggests the modern universe really is expanding faster than the early universe predicts it should. The leading explanation is something called dark energy, but that's less an explanation and more a name we gave to our ignorance. And here's why the stakes matter personally. If the expansion rate is as fast as modern measurements suggest, and it keeps accelerating, the eventual fate of the universe is something physicists call the Big Rip, where dark energy becomes strong enough to tear apart galaxies, then solar systems, then atoms themselves. Not in our lifetime, but the trajectory is there in the data Webb is collecting. So we've built the greatest telescope in history, pointed it at a fundamental question, and the main thing it came back with is, it's worse than we thought. Rogue planets everywhere. There are planets out there with no star, no sun, no warmth, just mass, drifting through interstellar space in permanent darkness, untethered from any system. We knew these existed in theory. What we didn't know is how many of them there are, or that some of them travel in pairs. Webb found over 40 rogue planets in the Orion Nebula region alone, from a patch of sky roughly the size of your thumbnail held at arm's length. That's already a lot, But the genuinely baffling part is that a significant number appear to orbit each other, drifting through space as binary pairs with no star anywhere nearby. This shouldn't happen easily. Rogue planets are typically ejected from their home solar systems through gravitational interactions, kicked out like billiard balls. The fact that some of them are gravitationally bound to each other suggests either they formed independently of any star, or they captured each other in open space under conditions that shouldn't be that common. Neither explanation sits comfortably with current models. The implications for the search for life are genuinely unsettling. If rogue planets are this common and some retain internal heat or host subsurface oceans, then habitable environments might exist in the dark between stars in numbers we never considered. Planets, apparently, don't always need a sun. Some of them just roam free. The universe is considerably stranger than the textbook diagram suggested. Gravity as a telescope. There is a galaxy so far away that the light reaching us from it has been traveling for 13.4 billion years. The universe itself is only 13.8 billion years old. We should not be able to see this thing. And we only can because Webb is using the universe's own mass as a magnifying glass. The technique is called gravitational lensing, and it works because massive objects like galaxy clusters warp the fabric of space-time around them. Light from objects behind the cluster gets bent around it, sometimes amplified, sometimes stretched into arcs, and occasionally focused directly toward us in a way that makes a distant galaxy appear much brighter and larger than it actually is. Webb has used this to confirm the most distant galaxy ever observed, a galaxy called JADES-GS-Z14-0, which existed only 320 million years after the Big Bang, a time when the universe was still, by cosmic standards, a newborn. The light hitting Webb's mirror from that galaxy left before Earth existed, before the Sun existed, before our solar system was even a cloud of gas. It has been traveling for longer than life has existed on this planet, and we can see it because of a phenomenon Einstein predicted in 1915, using galaxy clusters we didn't know existed as a lens we didn't build. The way Webb sees the earliest moments of cosmic history is by borrowing the universe's own furniture. By the way, if you're finding this as wild as I am, I post content like this regularly. I'd really appreciate it if you subscribed. Thanks. Dead stars still glow. When a massive star dies in a supernova, it doesn't just disappear. It leaves behind a turbulent, expanding shell of gas and debris that can remain visible for thousands of years. And Webb has now given us the clearest look ever at one of the most famous of these remnants. Cassiopeia A is the remains of a star that exploded roughly 340 years ago. Astronomers have been studying it for decades. Webb looked at it and found something nobody expected. A large, bright feature inside the remnant, glowing in infrared in a way that doesn't match any of the existing models for how supernova debris should behave. Researchers have taken to calling it the green monster, a real designation used in published work. We don't fully know what it is. The leading theory is that it's a structure formed by the shock wave of the explosion interacting with material the star shed before it died, but the details don't quite fit. What's not in dispute is the speed of what Webb is observing. The shock wave from Cassiopeia A is still expanding today, racing outward at roughly 6 million miles per hour. It has been doing that for 3 centuries, and it's not slowing down appreciably. The entire remnant spans about 10 light years, and Webb can now resolve structures inside it smaller than our solar system. We have a dead star. We took a very good picture of it, and now we have more questions than before. Genuinely helpful. Atmosphere of death. For years, the TRAPPIST-1 system was the most exciting address in the search for extraterrestrial life. 7 Earth-sized planets, 3 in the habitable zone, relatively close at 40 light years. Scientists spent a lot of energy being hopeful about it. Then Webb looked at one of them and came back with bad news. TRAPPIST-1b is the innermost planet in the system, and Webb's infrared measurements of its dayside temperature suggest it has essentially no atmosphere. A planet with no atmosphere can't moderate temperature, can't support liquid water on its surface, and can't protect any potential biology from the star's radiation. The day side of TRAPPIST-1b hits around 450 degrees Fahrenheit, which is consistent with bare rock baking under direct starlight, with nothing to trap or redistribute heat. The planet is also tidally locked, meaning it doesn't rotate relative to its star. One side is permanent noon, The other side is permanent midnight. There's a ring of perpetual terminator twilight between them, but without an atmosphere to move heat around, even that region is probably brutal. TRAPPIST-1b orbits closer to its star than Mercury orbits the Sun, which helps explain the harsh conditions, though TRAPPIST-1 is a much dimmer red dwarf. The most Earth-like planet on practically everyone's shortlist turned out to be about as hospitable as the inside of a kiln. The other TRAPPIST planets are still being studied, and the first answer wasn't the one anyone wanted. Something ate a star. A black hole tore a star apart and swallowed most of it, and Webb watched. This is called a tidal disruption event, a clinical name for something genuinely violent. A star wanders too close to a supermassive black hole. The gravitational difference between its near side and far side exceeds the forces holding it together, and the star gets stretched into a long stream of debris spiraling inward. What Webb added is what happens next. As the material falls in, not all of it gets consumed. Some of it gets launched back outward as jets, moving at a substantial fraction of the speed of light, fired by the magnetic fields around the same object that just destroyed the star. Webb's infrared sensitivity let it peer through the dust that typically obscures these events and observe the debris disk and outflows in detail no previous telescope could manage. The black hole responsible is millions of times more massive than the Sun, the kind of object where our entire solar system, orbital paths included, would fit inside the event horizon. At that scale, the tidal force that shredded the star operated across tens of millions of miles. The star didn't fall in gradually. It was pulled apart faster than sound could travel across it. A star fell into a black hole, and the black hole immediately started throwing some of it back. Even at the event horizon, there are leftovers. Ocean worlds confirmed. There is a moon orbiting Saturn that is actively shooting its ocean into space, and Webb has now confirmed the plume is dramatically larger than anyone realized. Enceladus has been known since the Cassini mission to have geysers venting water vapor through cracks in its icy surface. What Webb found is that the plume isn't just a local phenomenon around the moon. It stretches more than 6,000 miles into space, roughly the distance across the entire continental United States laid end to end, pointing straight up from the surface. That water isn't just falling back down. Enceladus is feeding it directly into Saturn's E-ring, replenishing it continuously. Webb also detected organic molecules mixed into the plume, including compounds that on Earth are associated with the chemical reactions that produce the building blocks of life. That doesn't mean there's life in Enceladus's ocean, but it means the ocean is chemically active, which is exactly what you'd want to see as a first condition. The ocean contains more liquid water than all of Earth's oceans combined, locked beneath an ice shell several miles thick, kept liquid by tidal heating from Saturn's gravity. Enceladus has been shooting its ocean into space continuously, and has probably been doing it for billions of years. Nobody told us it was this dramatic. Black holes at dawn. The early universe should have been full of small things slowly growing into larger things. Gas clouds collapse into stars. Stars die and leave remnants. Remnants eventually seed black holes that merge and grow over billions of years. That's the timeline. Webb found supermassive black holes, objects hundreds of millions or even billions of times more massive than the Sun, existing less than 1 billion years after the Big Bang. That's not enough time. By the physics we currently have, a black hole can only consume mass so fast before the radiation it produces pushes the infalling material back out. This is called the Eddington limit, and it sets a hard ceiling on growth rate. For the black holes Webb is finding to have reached their observed masses within the available time, they would have had to accrete essentially continuously at or beyond that limit from the moment they formed. One leading idea is that some black holes formed directly from collapsing gas clouds, bypassing the stellar stage entirely. We've never confirmed one. Webb is actively looking. We built the most powerful telescope ever made specifically to look back in time. The first thing we consistently keep finding is black holes that aren't supposed to be there yet. Carbon found nearby. Europa is one of Jupiter's moons, and it has been on the short list for potential life in our solar system for decades. It has a confirmed liquid water ocean beneath a shell of ice. It has tidal heating from Jupiter's gravity, and it's been showing signs of geological activity. What nobody expected was for Webb to look at Europa's surface and find carbon, not just trace amounts. Webb detected carbon dioxide and complex carbon compounds on the surface, specifically concentrated in a region called Tara Regio, which is a geologically young area of disrupted terrain. The distribution matters as much as the detection. The fact that the carbon compounds are concentrated in a tectonically active region strongly suggests they didn't arrive from meteorite impacts or external sources. They appear to have come up from below, which means the subsurface ocean isn't just water, it's chemically active water, with carbon cycling between the ice shell and the ocean in a way that could support complex chemistry. On Earth, carbon is a prerequisite for every form of life we know. It's the backbone of every biological molecule, and it's showing up on a moon with a confirmed subsurface ocean. Webb pointed at one of Jupiter's moons and found carbon sitting on the surface, just sitting there, like a receipt left out in the open. Time runs different. The gold in your jewelry was forged in a place where time ran slower than it does on Earth. Not metaphorically. That is the actual, measurable physics of what happens near objects massive enough to warp space-time. Einstein predicted this over 100 years ago. Webb is now giving us data to watch it happen at cosmological scale, and the implications are stranger than most people realize. When two neutron stars spiral into each other and merge, called a kilonova, the collision happens under gravitational conditions so extreme that the atomic nuclei being fused are experiencing time at a slower rate than we are. The heavy elements forged in those collisions, including gold, platinum, and uranium, are the products of nuclear physics happening inside a gravitational time dilation field. Webb has observed kilonovae and their afterglows with enough detail to track specific elements being produced. One kilonova produces more gold than exists in all of human history. The neutron stars involved have densities so extreme that a teaspoon of their material weighs more than 1 billion tons. Not the combined mass of both stars, a teaspoon of either one before the merger. Every heavy element in your body heavier than iron was produced in a place where time moved differently than it does here. Webb is the first telescope powerful enough to watch this happening in other galaxies and confirm the physics in real time. We built the best eye in human history, pointed it at the sky, and what it keeps showing us is that reality is significantly weirder than we built our intuitions to handle. If that sent you down a rabbit hole you're not ready to climb out of, consider subscribing so you don't miss what Webb finds next. Thanks for watching.